Don't forget to subscribe and ring that bell.
Well, howdy there, partner. Welcome back. If you're returning, if this is your first time, welcome to the 2008 AP Calculus AB practice exam. We are going to start section 1, part B. These are the multiple choice questions that get a calculator. Yay! Good for us. All right, we are going to cover 9 of these 17 questions today. That will cover questions number 76 through 84. And speaking of calculators, I use the TI 84 Plus CE, the color edition. I love it. Got a classroom set of it. I have a personal one that I use. It's mint green. Love it. Links in the comments below if you're on the market for one. They got a whole slew of colors. They're definitely worth it if you need one. All right, let's get started. Number 76 reads, a particle moves along the x-axis so that at any time where t is greater than or equal to 0, its velocity is given by v of t, which equals t squared times the ln of t plus 2. What is the acceleration of the particle at time 6? We want acceleration at 6. But first, we need to know that acceleration, okay, of t, well, that's really the derivative of velocity. And it's a great thing we get a calculator here. So I am going to go to my calculator. All right. View detached LCD. Why not? And the calculator will give us the derivative as long as we have a number to plug in for our variable of time. Our calculator will not give us an expression that's the derivative, but it will output a number if we have an input for that derivative. What do I mean? I'm going to go to Math 8. We're going to use x as our derivative. I'm going to put the equation for what I want to take the derivative of. In this case, I'm going to put velocity in there. The calculator will take the derivative and input the number for time, or in this case, for our x value. All right, so we have x squared times the ln of x plus 2. All right, and I want an x value, okay? I want times 6. Okay, so I want my x value to be 6. Now, without inputting a variable, a number in for that variable, it won't give me the expression. It won't use the product rule and say it's x squared times the derivative of ln of x, which is 1 over. It won't give us an expression or an equation, but it will give us a number. And that number is 29.4532. Okay, and you know, all these answers seem to go 3 decimal places. So 29.453. Oh, look at that. It is choice C. Very easy with a calculator. Number 77. If the integral from 0 to 3 of f of x dx is 6, okay, and the integral from 3 to 5 of f of x dx is 4, then the integral from 0 to 5 of 3 plus 2 f of x dx is what? Okay, this problem we don't need a calculator for. We just need to know our rules for integrals, specifically when it comes to bounds. Okay, so they're asking me from 0 to 5. So let's kind of break this down. And then we can use both of the given integrals and their values to solve our problem, okay? So I'm going to take the integral. Okay, I'm going to start with this. Okay, and I know I can integrate 3, and I can integrate this separately. All right, I can just go down the line. So that's what I'm going to start with. So I'm going to start by saying it's the integral from 0 to 5 of 3 dx plus the integral, all right, of 2f of x dx, also from 0 to 5. What I'm going to do here, though, is I'm going to take this 2, since it's a constant, and put it on the outside. All right. Now, the integral on the left, right now, I should say currently, the integral on the left, I can integrate that. That's an easy thing to integrate. All right? So let's just go ahead and do that right now. So this is just 3x, and I want that from 0 to 5. Okay, so it's 3 times 5, the upper bound, minus 3 times 0. That's 15. So this part right here is 15. So let's not forget that needs to be added to whatever I get here. All right? Okay, so let's see. Above, I don't have an integral that goes from 0 to 5. But I have an integral that goes from 0 to 3. And I have an integral that goes from 3 to 5. So in case you can't make this connection, I don't know what f of x is. Let's say it looks like this. All right, this is f of x. Here's 0 to 3. I have one integral. And then I have another integral that goes from 3 to 5. Okay? So my integral in green goes from 0 to 3. So it's all this. That area under the curve. That's some number I'm going to get. In this case, they tell me it's 6. That's 6. And then I have the integral that I underlined in red that goes from 3 to 5. That's all this area. And that's a value, they tell me, it's 4. All right? So if I want an integral that goes from 0 to 5, I can just add these together. Okay? So my integral here from 0 to 5, okay, is really, I think, the integral from 0 to 3 of f of x dx. And I add that to my integral from 3 to 5, because that will cover everything of f of x dx. And that is 6 plus 4, which is 10. Okay, so this integral is 10. Don't forget, I need to multiply it times 2. So that's going to be 20. And oh, let's not forget, I still need to add this to my 15. This part was 15. This part is 20. When we add them, we get our 35. Okay? And as is typical, the answer is choice D. A lot of the problems where you get to use a calculator, you either can't or don't need to use a calculator for some of them. Number 78. For t being greater than or equal to 0, h is a differentiable function of t that gives the temperature in degrees Celsius at an Arctic weather station. Which of the following is the best interpretation of h prime of 24? And you have all these words, and you need to be careful with the way all of these responses are worded. Meaning, when I take a look at this, that's the rate of change of h. And what is h? That's degrees Celsius, okay? Degrees Celsius. So it's a change in rate, and T represents some temperature, change in rate. T is hours. I'm sorry. I saw T for temperature here, but really T is hours. And that's a change in temperature in Celsius. So it's in degrees Celsius per hour. All right? So H prime of 24, it's the rate of change of H, which is in degrees Celsius per hour, right, okay, right at the 24th hour. Okay? I want the rate of change specifically at 24. Okay? So is it the change in temperature? No, it's not the change in temperature. It's the rate of that temperature. Okay, so it can't be this. I don't see rate anywhere here for choice B either. Okay, the average rate at which the temperature changed during the 24th hour. No. Average rates would be a change in Y over a change in X. This is the instantaneous rate at one point, right at that 24th hour. So it's not the average. All right, let's take a look at D and E. The rate at which the temperature is changing during the first day. Well, the first day would represent from time 0 to time 24. So it's not the first day. It is the rate at which the temperature is changing right at the end of the 24th hour choice E. Number 79. Oh, this is going to be good. It starts out with a spherical tank. Okay, contains 81.637 gallons of water at time t equals 0. This looks like it's going to be pretty important. Time t equals 0 minutes. It already has 81.673 gallons of water. For the next 6 minutes, water flows out of the tank at a rate of 9 sine of the square root of t plus 1 gallons per minute. How many gallons of water are in the tank at the end of 6 minutes? All right. So first of all, I know we start with 81.637. This is at time equals 0. This is our gallons at time equals 0. This is where we start. We're losing water these 6 minutes. So we got to subtract some value. Okay, we're going to have less than 81. Okay, so you know it can't be choice E. That's more. We're going to have less than 81. Now the rate is represented by this equation here. That's in gallons per minute. But I want to subtract. Remember what I said? This is gallons. I want to subtract also gallons. Okay, whatever gallons I subtract. I've written this on several of these videos, okay? We have position, velocity, and acceleration. These are all one derivative away, okay? But if I go backward, that is integration, okay? I go backward, that's integration. But we get so ingrained in our brain to look at position, velocity, acceleration, that really we should also look at it as units, okay, unit per time, and then unit per time squared. Same things apply. In this case, we have gallons per minute, but I want gallons, okay? So I'm going to go backward, which means I need to integrate my rate of gallons per minute to get those total gallons. And I'm going to integrate it from time 0 to time 6 because at 6 minutes. That will give me this value that I'm going to subtract. I don't want to subtract a rate because I have gallons. I want to subtract gallons. So right there is going to be the integration from 0 to 6 of my rate, okay, which is 9 sine of the square root of t plus 1. And of course, there's our dummy variable. I'm going to just put that in a calculator. And then I'm going to start out with 81.637 and subtract that number right there. In fact, I don't have to do it separate. I could do it in one go about. So I can just start with 81.637 and subtract. I go to math number 9. The integration from 0 to 6, all right, of our equation for the rate, which was 9 sine of the square root, and we're using x's, so x plus 1, pop out there. Don't forget our dummy variable, dx. And we get 36.605. That 5 will round up to a 6. Okay, so let me do this. I kind of minimize this, get it kind of down and out of the way. This will become 36.606. Okay, whenever I subtract it, whatever that number is, whatever this was, I already subtracted it in the calculator. Okay, I already did the math in the calculator. So it should result in 36.606 gallons remaining at the end of 6 minutes. Okay, and that, my friends, is choice A. All right, so in summary, we've done 4 problems already. 2 of them we needed a calculator for, and 2 we couldn't even use a calculator. I mean, we could have when we were adding 15 and 20, but I mean, we didn't need to do that. Let's take a look at number 80. A left Riemann sum. Okay, this is important. They're telling us right off the get-go. A left Riemann sum, a right Riemann sum, and a trapezoid sum are used to approximate the value of the integral from 0 to 1 of f of x. Our graph of f of x is below, okay? Each using the same number of subintervals. So the only difference is the method, LRAM, RRAM, and trapezoid, all right? The graph of the function f is shown in the figure, well, below and to the right, not above. Which of the sums gives an underestimate of that integral? Okay, so it might be 1, it might be more than 1. All right, so what we're going to do here is I'm just going to kind of just sketch what I have. We have something that goes like this, from 0 to 1, like that. Here's 1, here's 0. If I use an LRAM, okay, let's say I break it up just for the sake of argument into 2 subintervals. Doesn't matter as long as I use the same number. Well, LRAM would go up to here, would hit at the left corner. That's 1, this area. And then this is the left corner. That's pretty much flat. So look at all this space that does not get included. Okay, that is definitely going to be lower than the actual. That is lower than the actual area if I were to just do an integration. So which sums gives an underestimate? Well, this one definitely does. The left sum does. Let's try RRAM, or the right sum. Same little graph here. Going to sketch this from 1 to 0, and we'll break it up into 2. Okay, now I'm going to do the right sum here. Okay, so this rectangle is a right sum right there. And this rectangle, I do the right corner touches it. So I am, oh man, all right, I am going to count all this area. Okay, that's obviously more. That's above the curve. That's an overestimate of what it should be. Remember, my curve goes from here and everything below. Okay, but look at those corners of those rectangles that are above that. That is an overestimate. They're asking us for an underestimate. So this definitely is an overestimate. So 1 has to be in the answer, but not 2. Okay, 1 is there, but not 2. So it's either just 1, or it's just, oh, it has to be 1. It can't be this 1, it has to be there. So it's either 1 only, or 1 and 3. Let's do a trapezoid rule, okay, on this curve, on the one that's pictured there, and I will do that in purple because, you know, I've underlined that in purple. Trapezoid, we'll break it up into 2. Here's 1 point. Here's the other point. It would be under the curve. Look at that. Okay, then here's 1 point. Here's the other point. This line would also be under the curve. So I'm doing this. That's one trapezoid. Here's another trapezoid. I clearly, there's some stuff like right above the trapezoid that's under the curve that I don't get. So it will really be actually less than the actual area, which means that will also be an underestimate. So it's 1 and 3, which is choice D. Another problem that we get to use a calculator for, but we really can't use a calculator for. Number 81. The first derivative of the function f is given by f prime of x, which equals x minus 4e raised to the negative sign of 2x. How many points of inflection does the graph of f have on the interval from 0 to 2 pi? You need to be able to make the association that points of inflection, it's where the second derivative, not only is it 0, but it changes from positive to negative or negative to positive around that 0. Okay? So the second derivative is the slope of the first derivative. So what I'm going to do, okay, I can find out what the second derivative is, and I can graph it, okay? Or I can just graph the first derivative and realize that the slope of the first derivative is the second derivative. So what does that mean? That means that if I want to know when the second derivative goes from positive to negative, I just got to find out when the slope of the first derivative goes from positive to negative. It means it would go increase to decrease. And same thing here. If I want to know where the second derivative goes from negative to positive, I just look and figure out when the slope goes from negative to positive. That means it goes down and up. And that's the way I'm going to do it, okay? The least amount of work, the better. Let's graph our first derivative. All right. Turn this bad boy on. Come on. Go to y equals. And the equation they give me is x minus 4e raised to the negative sign of 2x. And I want that in my window from, again, they give us an interval from 0 to 2 pi. So it's 0, and I'm literally going to type in 2 pi. Why wouldn't I? Because I have a calculator. I'm going to graph that. All right. We got this little funky thing here. Oh, look at you. You little vixen, you. Keep on trucking. Keep on trucking. Boom. Let's bring this out so we can draw around it. Now, anytime I have a graph of the first derivative, I know it's the first derivative, but I still write it here. My first derivative is my y value. I want to see where the slopes change. That's what I'm looking at right here. Okay, where the second derivative changes or the slope of the first derivative changes. Ready? Positive slope here, negative slope here, which means one inflection point. That's where it changes. That's the first one. It's not at x equals 1. I'm just saying that's our first one. Negative slope to positive slope right here. Oh, boy. We have another inflection point right there. It's our second one. Go from positive slope to negative slope. Oh, boy. That's number 3 right there. And last but not least, I go back to a positive slope here. So that's our fourth point where our second derivative changes, or the slope of our first derivative changes. There are 4 points. They don't ask us what they are. They just ask us how many we have. And there you go. That's a great one to use a calculator for. Number 82. If f is continuous function, if f is a continuous function on the closed interval from a to b, which of the following must be true? Okay, let's take a look at these one at a time here. And these ones, I think the explanations take more, all right, than the actual knowledge. If you know what you're doing, this is a quick one, right? A, there is a number c in the open interval from a to b such that f of c is 0. This is saying, well, at some x value, I'm going to have a 0, a y value of 0. That is this must. That doesn't have to be true. I can graph something here with on an interval that does not cross the x-axis or have a 0. That it could be true, but it doesn't have to be true. When they say it must be true, okay, let's see. I'm going to start doing this, okay? Here we go. Here's 2 points, A and B. Okay, so we have some blue one. I can draw something where it doesn't have a 0, where y is 0. Doesn't touch the x-axis, okay? B, there is a number c in the open interval such that f of a is less than f of c, which is less than f of b. I can certainly, the blue line proves that, but does it have to be true? Okay, so let's do this one in red. Does it have to be true? No, I can draw a line that goes like this. If that was the case, this would be opposite. This would be the smallest, this point at B. This would be in the middle, okay, and this would be the biggest. So I can draw a line like that, okay? So B isn't true. It doesn't have to be true. It could be. Remember, this must be true. C. There is a number C on the closed interval from A to B such that f of c, you have a y value, that's greater than any of the other x values of f of x for all of x in this interval. Let me try this in green. Okay. All right. I don't know. Why don't we do something that goes like this, then comes down, then up? Okay. What they're saying is there's some value where my y value is bigger than everything else. What they're really saying is there's a maximum point there. Okay? Yeah. For the green one, here's the maximum point. Guess what? For the blue one, here's the maximum point. Guess what? For the red one, here's the maximum point. C has to be true. How come? Because it's continuous. There are no breaks and there are no arrowheads because there's an interval. It stops and ends at A. All right? So let's take a look at the other two, just in case you had a question. Let's do the next one in this orange. All right? There is a number C in the open interval, so since the derivative is 0, okay, that means it has to have a horizontal line. So at some point it goes like this, horizontal and up. No, the red and blue ones don't do that. No, I don't have to have a horizontal line in that graph I draw. It doesn't have to be. I mean, it can be, but it doesn't have to be. My biggest, I guess, thing that I looked into that I really had to look at this question at was E. Because some people will say, how come it's not E? And let's go to the gray, all right? There is a number C in the open interval such that the derivative is the same as the average rate of change for my endpoints. That's a rule, isn't it? If something, okay, does not have any breaks or gaps in it, there has to be a point in between that is the average of the slopes of the endpoints. It's a mean value theorem. But here's the one catch. This is true. This has to be true if it is differentiable everywhere. I know that's one word, everywhere. Look at the problem. It tells you that it's continuous everywhere. It doesn't say it's differentiable. Remember, if it's differentiable everywhere, then sure, it's continuous. But if it's continuous, it doesn't mean it has to be differentiable. Really? Yeah, a corner, a cusp, or a vertical tangent line. So let me do this. I'll draw one right now. Here, it comes up, down. That's continuous. Guess what? There's a corner. I can't take the derivative of that corner. Little tricky the way they did that. It can't be E because it doesn't say it's differentiable anywhere. It just says it's continuous. And just because it's continuous doesn't mean it's differentiable. If that word continuous that I circled in gray in the problem said differentiable, then yes, choice E would have to be true. Number 83. The function f is differentiable and has values in the shown table above. Have I ever told you how much I love graphs and tables and charts? Oh, I do. Both f and f prime are strictly increasing. This is good, okay? On the interval from 0 to 5, which of the following could be the value of f prime of 3? All right, f prime of 3. This right here. Okay, what could be the direct f prime? Okay, so what would be here at 3? All right, well, here you go. This is what I'm going to do. I am going to 3.0 to 3.1. Oh, dirty what they did. All right, so I'm going to take the derivative. Okay, I'm going to take the derivative between these 2 points. Okay, and then I'm going to take the derivative of these 2. All right, and I'm just going to kind of figure it out. All right, and I don't. Why can't I just take the derivative, take this, and figure it out? I'll explain in a minute, okay? Because it says it's always increasing, I need to compare 2 slopes. They should always be positive. Not only should they be positive, they should be rising in positive, okay? So if I take the derivative of this green one here from 28 to 2.8. So I'll see my change in y, it's 45 minus 39.20 over 3.0 minus 2.8. What do I get? I get, oh my God, it's 0.8 plus 5. Is that 5.8 divided by 0.2? That's 29. It's 30, 29. Oh, it's 0.2. 534. Let's just put this in the calculator. I think I'm right here, but let's make view attached LCD. Where are you? There you are, my friend. Okay, I'm going to go. Oh, well, let's get out of here first. clear this. Alpha y equals, enter. I've got 45 minus 39.2 all over 3 minus 2.8. Okay, that's 29. So that gives me 29. All right? That's the slope of this green one. Okay, now let's do the red one. It's going to be 48.05 minus 45 all over 3.1 minus 3.0. That's 3.05 divided by 0.1. That's 30.5. Okay? If the slope is increasing, if the slope is always increasing, it can't be 29. So if you would have just done the green, say 29, oh, it's there. Or if you would have just done the red, okay, and say 30.5 is there. No, it has to increase. So it has to be bigger than 29, but it can't be bigger than 30.2 because as it goes up, it increases, which means this has to be bigger and this has to be smaller. And the only value on this list that's in between 29 and 30.2 is 30. Okay. Well, why can't I pick 29? 29 is not bigger than 29. It's the same. Why can't I pick 30.5? Because 30.5 is the same as 30.5. It's not less than because it has to be there. Okay. I've rarely seen, this is an oddball. I see problems where I pick little points close to it to approximate a slope. But because they say f and f prime are strictly increasing, the slope, it has to be increasing from here. So it has to be bigger than 29. And whatever I get here, it has to keep on increasing. So this number after has to be bigger. So it has to be sandwiched in between those two values. Wow, I end with a chart and a graph? I've been living right every day to get something like this. I've been living life right. The graph of f prime. Okay, well, I'm going to immediately do this. Well, y equals f prime. Any y value is the value of the derivative. Okay? The graph of f prime, the derivative of f, is shown above. On which of the following intervals is f decreasing? F is decreasing, okay? F is decreasing when f prime is less than 0 or it's negative. If y is the value of f prime, I just want to see when y is negative. From 0 to 2, and then from 4 to 6. Man, that was a gimme. That was the biggest, that was beautiful. We're done. That was a good one to end with. Look it. You're going to do good on this exam. You and I, buddy, we're going to do good on this exam. Thanks for hanging around. Thanks for playing calculus. And I will see you for the next video. Like the video, ring the bell, subscribe, because that's the only way you get notifications of the future videos that go up. Bye-bye.
Don't forget to subscribe and ring that bell.